Hi everyone, welcome to this video, and we'll be talking Kirchhoff's voltage law, or KVL in short, in electrical circuits. So let's dive into the KVL rule first for some time, and then we'll start solving some questions. So in a sense, as the slide suggests as well, Kirchhoff's voltage law states that the algebraic sum of all voltages around a closed loop is zero. Essentially, we're now dealing with loops in electrical circuits. As you can see here in this circuit, we have several components that are connected together in series, and they create a single loop where you can start from any arbitrary point and try to make a turn, and you'll return to your original position. And in that case, you can assume that all of the voltages, whether it would be from the voltage sources like V1 or from the voltage drops like V2 and V3, when they are summed up with each other, they would result in the value of zero altogether. And the way that actually this will be calculated is with respect to the direction of entrance to that element as well. So it really matters actually when you start turning clockwise, for instance, when you enter from which terminal of this component that determines the sign of that voltage. So in a sense, when you enter from the negative terminal, you consider that voltage source to be negative. However, when you enter from the positive terminal of the component, you would consider that voltage to be positive. In that sense, when we start writing down an equation for this loop and consider a clockwise direction, starting from the bottom left as a reference point, we have minus V1, since the entrance to V1 is from the minus or negative terminal. Moving forward, we have plus V2 because we enter from the positive terminal of V2. Moving forward, it will be V3. As long as we move clockwise, we enter from the positive terminal of V3. Then moving down through V4, from the negative terminal, we have minus V4. And finally, moving from right to left through positive terminal of V5, we can have plus V5. And finally, we arrived at our original reference point. Then that's enough actually for us to call all of the summation to be zero. That's pretty much everything about the KVL rule, that we'll be using that in solving questions for the electrical circuit analysis, such that this would help us to find out the currents and voltages of nodes and loops. So let's get started in solving this question. We'll be using KVL rule here in order to solve this question. In a sense, we have a complicated circuit that has several loops. As you can see here, essentially you can name I1, I2, and I3 corresponding to three different loops. And this has several independent sources as well, such as 8-volt and 6-volt sources, as well as several resistors. So in order to solve this, so using the KVL, we need to write KVL for each loop separately. So in order to use the KVL for this, though, we also need to consider what is the amount of the current that is passing through each element, because that would be what creates the voltage drop through that element as well. So if you assume that I1 is rotating clockwise on the top loop, I1 is holds true. This holds true actually when I1 is passing through 10 ohms. But when I1 gets into this node, we need to consider that how much of I1 is going to pass to the left, or how much is going to be passed downwards. So that is something that we need to decide first. So we will label all of the currents that we need in our analysis before getting into the solving and writing down the KVL equations. So imagine that as we started, so I1 is moving up and to the right and to the down of downwards through loop 1. So, and also I2 is moving up through 4 ohms. So at this node, we obviously see that I2 is going to be subtracted, minus I1 is going to go to the right direction. So it will be I2 minus I1. So if you consider the node on the right side, you can easily see that I1 is flowing downwards into that node. And also I3 is exiting that node. So we would call it I3. And this node, we can easily find out that I1 minus I3 is flowing to the left side. I1 minus I3. So we're trying to reduce the labeling down to only I1, I2, and I3. However, at some point, we might have some other currents such as I that we need to write that down in terms of I1, I2, and I3. For instance, at this node itself, we see two currents are coming from left and right, and their summation is going to flow downwards in a sense, ignoring the value of I. So the current from left to right is I2 minus I1. The current from right side is I1 minus I3. And their summation, when you sum them up, you can easily see that I1s are going to be cancelled. And what is left is I2 minus I3 that is going to flow downwards. So I would write I2 minus I3. So that is the current that is flowing downwards. Now, now's the time to find out what are all of the KVLs that we can write for this circuit, starting with loop 1. So loop 1 is essentially what I'm going to highlight that as well. So this is all about loop 1, and I'm color coding that for better visibility as well. For loop 1, what we can write is to start from a position. It can be an arbitrary position, but in our case, I would choose this one and try to flow clockwise such that it's according to the direction of the current as well. And when we hit any resistor, there will be a voltage drop across that. And when we hit any voltage source, there will be a voltage increase or decrease with respect to that voltage source as well. And we would start with the, from this point, flowing clockwise with respect to I1. This 10 ohms, the voltage drop across that is going to be simply with respect to Ohm's law, 10 multiplied by I1. And since this is in the direction of the current flow, we enter from the positive terminal of that voltage drop. So it essentially would be 10 I1, as you can see here. So starting with 10 I1, moving forward, we have this 6 volts, but when we enter from the negative terminal, we need to consider minus 6. Moving forward, we have this 2 ohms, but then this 2 ohms is going to be multiplied by this current, I2 minus I1, which is flowing to the right side. However, we are moving to the left side. Now, since these two directions are contradictory, we need to consider the negative voltage drop across 2 ohms. It's obvious that the voltage drop is going to be from the high voltage to the low voltage when you consider the current direction. And if the I2 minus I1 is going to be positive value, the voltage drop across that is going to be positive on the left and negative on the right. And when we enter from the right side, we first see this negative terminal. That's why that we need to multiply a negative sign to 2 ohms multiplied by I2 minus I1. So we would have minus 2 times I2 minus I1. Since we arrived at our original position, we can then conclude this summation as 0. So that is our first loop. Let's move on and think about the second loop, which is going to be here. I'm going to highlight that with another color to have a better visibility. So it would be this green loop that we'll be talking about, loop 2. Now for that also, we need to start from an arbitrary position, and in this case, I would choose this bottom point, and flowing according to this I2, we need to first go up. The voltage drop across this 4 ohms is in the direction of this current flow. So the positive terminal is going to be on the bottom and negative terminal is going to be on the top, since the voltage drop is going to be from positive high voltage to the low voltage when with respect to the current flow. So it would be 4I2, that is, we would start with the positive 4I2 with a positive sign. Moving forward, we have this 2 ohms that is right now in the direction of the current flow as I2 minus I1. So we would have positive 2 times I2 minus I1, 2 times I2 minus I1. Now we need to flow downwards. So looking downwards, we have 1 ohms that is with respect to this I2 minus I3 current. It's in the direction of the current flow, so we would enter from the positive terminal. So we need to multiply positive 1 times I2 minus I3, I2 minus I3. Then we need to consider this 8-volt independent source as well. Since we enter from the positive terminal, we need to consider that as positive 8. And when we end up at our original position, we can conclude this loop as well. Now let's move forward with the third loop, and I'm going to highlight that with another color to elaborate the differences between the different loops. So right now, I would start from this arbitrary position at the bottom right, and according to this current flow, we need to first go left and upwards. We first hit this voltage source with the negative terminal, so we need to consider that with minus sign. So minus 8 volts, or loop 3. We have minus 8 volts, and afterwards, we need to look up again. There is a 1 ohm resistor, which is against the direction of the I2 minus I3. The current direction is against our flow direction, so we need to multiply a negative sign. So it would be minus 1 times I2 minus I3. Now we're here. We need to move clockwise. We hit positive terminal of the 6 volts, so we would consider plus 6. And we need to come down through this resistor. So 5 ohms times I3, it would be 5I3 plus 5I3 equals 0, since we end up at this reference point. So now we have 3 different equations, as you can see here, with 3 unknowns. So I1, I2, and I3 are the unknowns of these set of equations. The way that we would search for I1, I2, and I3 is first through the method of elimination. And the way that it really works is that we need to find out some variables with respect to the other variables. For instance, in the first equation, we have I1 and I2. So we can easily write down one of them with respect to the other one. So imagine that I1 is going to be calculated with respect to I2. Moving forward, we have the second and the third equation as well. So if you consider the second and the third equation, if we write down I1 in terms of I2, we would be having I2 here and I3, as well as I2 and I3. So we would have two equations that have only two unknown variables, and we can easily find out what those variables I are. So let's start with equation number 1. I would be just calling them different equations so that it would be easier for us to recognize and refer to them later. So we have equation number 1 that is allowing us to find I1, for instance, with respect to I2. So 10I1 plus 2I1 equals 2I2 plus 6. And 10 plus 2 is 12I1. Now, I can write I2, because that's easier for the calculation, 6I1 minus 3. So this would be my relationship between I2 and I1. However, if I replace that in equation 2, so I would say, let's call this one equation number 4 that we just got. Now, if I replace 4 in equation 2, what I would get, I'm going to reduce I2, so I would have only I1. So for I2, instead of I2, I would write 6I1 minus 3 plus 2 times I2. It would be 6I1 minus 3 and minus I1 plus I2 minus I3. It would be 6I1 minus 3 minus I3 plus 8 equals 0. So we need to just simplify this. We would have all of I1s. We have 24I1 plus 12I1 plus 6I1, and also minus 2I1. So let's consider them. 24 plus 10, it would be 34, plus 4, it would be 40. So 40I1, then let's just cancel them out. We'll be left with I3, that we have only minus I3 minus I3. Then our constants, 4 times minus 3, minus 12. 2 times minus 3, it's minus 6. So altogether minus 18. And minus 3, it's minus 21. Plus 8, so it will be 13 then. So minus 13 is going to be 0. So that is our next equation that we need to have, and I would call that equation number 5. Now that we have an equation in terms of I1 and I3, we need to do the same for this equation number 3. We need to repeat the same procedure by resolving the fact that I2 can be represented in terms of I1, and just replacing I2 with this value of 6I1 minus 3 here, then we would end up actually with another equation that has I3 and I1 only. So let's do that. So we would essentially consider equation number 4 in equation number 3. So we would have equation number 4 in equation. If you replace that in equation number 3, what we would get is minus 8 plus minus I1 minus I2, that instead of I2, we would write 6i1 minus 3, then plus i3, that we would have it plus i3 plus 6 plus 5i3 equals 0. Simplifying that, we have i1 with minus 6 only, so minus 6 i1. Then i3, we would have 1 and 5, so plus 6. Plus 6 i3. Our constants, by the way, are going to be minus 8 plus 3, it would be 11, plus 6, it would be 17. So plus 17. So that's how our next equation is going to be generated, and I'm going to call this as equation number 6. So you see that we have two equations, 5 and 6, that have only i1 and i3 as the unknown variables. So we can actually combine them together to easily find out what the value of i1 and i3 are altogether. So in order to do that, we can again make use of the method of elimination, but this time it's better actually to get i3 in terms of i1 and replace that in equation number 6. So we'll start from equation number 5 and try to find i3. So using equation number 5, we have i3 equals 13, no, it would be 40i1 minus 13. And now replace that in equation number 6. We would have minus 6i1 plus 6i3. So instead of i3, we have 40i1 minus 13 plus 17 equals 0. So essentially now we have one equation with one unknown variable, that is i1 only. That if you simplify this, you would get i1 to be around 0.24%, roughly. So that is i1's value after all of these calculations. And now that we've found i1, we can easily use this equation to find i3. So using 5 again, i3 is 40 times i1, which is 0.24 minus 13, which is around the value of minus 3. So i3 is around minus 3. Now that we have i1 and i3, we only need to find i2. And the easier equation for us to find i2 is this equation number 4, since we know i1 and we can implement that through equation number 4. So let's do that. Equation number 4, we have i2 equals 6i1, and i1 is around 0.24 minus 3. So it would be around minus 1.5. So this way we could find all of the currents that are flowing through different parts of this circuit. And in order to verify our analysis, we can easily double check our results as well. I1 is around 0.24 or about a quarter amp, which is flowing all the way here. And I3 is going to be minus 3, which means that 3 amps is going upwards and 0.25 is going downwards. So altogether, it would be 3.25 going to the left. So 3.25 is going to the left side. Let me just write it down with a black color, or with a green color. 3.25 roughly. Then we would have I2 minus I1 here as well. I2, we've got that to be minus 1.5, which means 1.5 is coming down. I1 is 0.25, so 0.25 is going up, 1.5 climbing down, so altogether 1.75 is going to the left side, because their summation is going to be I1 and I2. So 1.75, 1.75, and 3.25 going to the left. 1.75 of that is going to be reduced. What is left is going to come down, which is going to be around 1.5. And 1.5, if you consider I2 minus I3, I2 is minus 1.5, I3 is minus 3. So this summation is going to give us 1.5 as well. So this is a correct calculation for all of the currents. However, our original question was asking try to find I in this case, and I is nothing but the current that is moving upwards. The current that is moving upwards is exactly negative of I2 minus I3. So if you want to find out what is IO, I'm going to actually write it down at the very bottom. IO is, or I is simply negative of I2 minus I3. And essentially it is I3 minus I2. So I3 is minus 3, minus I2 is minus 1.5. So it is around minus 1.5 amps. Minus 1.5 amps upwards, meaning 1.5 amps is moving downwards. So that is pretty much everything about the use of KVL, or the loop analysis, or the mesh analysis, in calculating the currents of different loops, or even the voltage of different nodes. We so far could find all of the currents in all of the loops, and that would be through the process of elimination of the variables that we preceded the solution of this question. So now that we've got some idea about how to use KVL in solving a question, we have another example that I would be leaving out for you guys to have an exercise. And in this example, you'll be using the same procedure that I explained, using the mesh analysis. Try to find all of the currents, I1, I2, and I3 in this circuit. Try to consider unknown currents, for instance, the currents that are passing through this branch or the other branches that are sharing some currents from the loops with respect to original I1 and I2 and I3. And keep I1, I2, I3 as the only unknown variables that you would have, and try to solve it with the mesh analysis, or KVL, that we just explained. Thank you for watching. Hit like and subscribe to the channel if you enjoyed this video.